Oh boy. Yeah, sorry I'm late yet again. I wonder if I get in trouble with the university if I just canceled class today and said we all sleep for the next hour. Well, anyway, if you didn't see the email last night, we finished grading homework 4. We also finished our backlog of all the graded homeworks for people who turned stuff in late. So I believe everything that's turned in should be graded now. If you've turned anything in and it's not graded on Sakai, let me know and I'll try to figure out what happened. Also, homework 6 is posted on Sakai, which 2 of the questions from homework 6 are finals questions from previous years, just so you know what to expect. I'll try to post a copy of last year's final sometime soon, so you get some other idea, and I'll post the real final as soon as I get around to writing it sometime in the next day or two. It'll basically be due at the end of finals week. And remember, if you choose to write a grant, then you can skip all but one of the questions on the final. Anyway, today we're covering logistic regression. As I said, this is just another on our list of grab bag topics that I don't really have enough time to cover in the detail they require, but I wanted to at least give you an introduction to these topics if you ever see them in the future. And it helps if I turn my clicker on, doesn't it? So, recall the purpose of regression is that if you have a predictor variable or several predictor variables, a quantitative response variable, and you want to try to predict the response variable using these predictors. And in addition to making predictions, we may just want to say, is there a statistically significant association between a response variable and the given predictors? Is the association stronger than you would expect to observe by chance? And very powerful methods useful in a wide variety of circumstances, but it only works if your response variable is quantitative. In some situations, your response variable is binary, like say you have a list of risk factors, you want to know the probability that a person develops a given disease, that, say, lung cancer, for instance, smoking would be the obvious risk factor, but you could also look at things like age, family history, things like that. You may want to know, given all these set of potential risk factors, what's the probability that they'll develop the disease? Or what's the probability the baby will be born with low birth weight given some of the risk factors for low birth weight? Or given like a set of atmospheric measurements, what would be the probability that it's going to rain tomorrow? These sorts of questions can't be easily answered with the methods we've discussed thus far. Regular regression doesn't work because it assumes that your outcome variable is quantitative, whereas in this case your outcome variable is binary. And in some cases, when your outcome variable is binary, you can just use a t-test, but the t-test breaks down if you have more than one predictor variable. If you just wanted to say, if you wanted to do something like, well, you were doing lung cancer and smoking, in that case, both the predictor and the response would be binary. You could use something like a chi-square test. But if you wanted to, say, predict the probability of developing lung cancer given smoking plus age plus family history plus other risk factors, there's no simple way to use a chi-square test for that. And that's where logistic regression becomes useful. Recall, ordinary linear regression is you have a response variable y, you have a set of predictor variables, you try to predict the response variable based on a linear combination of the predictor variables. You just choose b0, b1, b2 up to bm, such that you minimize the sum of squared errors, that is, the difference between the observed y's and the predicted y's, square those, add those together, choose the b's to minimize that particular quantity. Well, this can be generalized to binary response variables, as I'll show you now. Let's say that we have a set of we have a binary response y, typically either 0 or 1. Say 1 means you have the disease, 0 you don't, and a set of predictors that are possible risk factors for the disease. Then we define a variable pi to be the probability that the ith response variable is equal to 1. So in other words, we're trying to predict the probability that the ith person is a case or not. And then logistic regression model is that we try to find a set of b's to fit this quantity as best as possible, log pi over 1 minus pi. And I won't go into the gory details of how you actually calculate this, but I mean the more obvious question is like, why on earth are we trying to calculate this log pi over 1 minus pi thing in the first place? That's a really bizarre thing to try to calculate. So why are we calculating all that log business instead of just, say, trying to predict these pi's directly? Why not just say pi equals b0 plus b1 x1i plus b2 x2i, and so on down the line? Well, the reason why you can't approximate pi directly is because probabilities always have to be between 0 and 1. And if we're assuming there's just a simple linear association between the predictor and the response, then we would say that, like, assuming that b1 in this equation is positive, we would want to assume the probability of being a case increases as the risk factor increases. The problem with that is that no matter how small b1 is, if x gets large enough, that's going to be bigger than 1. Likewise, if x gets small enough, you're going to end up with something less than 0. So if you just tried to predict the pi's directly as a linear combination of the xi's, you could very easily end up with predicted probabilities that are greater than 1 or less than 0, which isn't what we want. So basically, the way people try to get around this is, rather than try to predict these probabilities directly, try to predict the odds of a given event. That odds are defined such that if the probability of a given event is p, then the odds in favor of that event are defined to be p over 1 minus p. And I mean, the way you usually, the place you most commonly see odds nowadays are gambling, either in horse races or sports betting and things like that, is where you'll usually see this. If the probability that a given horse will win a race is 3 out of 4, then the odds this horse will win is 3 out of 4 divided by 1 out of 4, or 3. So that would mean there were 3 to 1 odds in favor of this horse winning the race. And the advantage to odds over regular probabilities is odds can vary anywhere between 0 and infinity. So as x gets larger, the odds can get arbitrarily large. We avoid that particular issue. However, odds still can't be less than 0. So if you had a really small x, you could end up predicting negative odds, which still isn't something that you want. But if you take a positive number and then take log of that number, then it will map to a number between minus infinity and infinity. So that tells us that if given the values of a set of risk factors, if we predict the log odds that that observation is a case, the log odds will be some number between minus infinity and infinity, which corresponds to a unique probability between 0 and 1. So the main reason, well, one of the reasons that people calculate log odds using logistic regression is that it means that you can take B0 plus B1 x1 plus B2 x2, your arbitrary set of predictors, and get a unique probability for any possible value of the x's. And there's some other methods that people have proposed to predict probability of an event based on a set of predictors like this, but logistic regression is far and away the most commonly used for various reasons. The others tend to be more difficult to interpret, and there's also some computational reasons when you try to calculate them in a lot of cases. So the overwhelming majority of the scientific literature will just use logistic regression. And this graph here just illustrates how you can map how any continuous number between minus infinity and infinity gets mapped to a probability between 0 and 1. Say you take your B0 plus B1 x1 plus B2 x2. If it turns out to be minus 2, that would get mapped to a probability of about 0.1. If it's minus 1, it looks like that's a probability of around 0.3. 0 would be 0.5, and so on down the line. Well, you see here that regardless of what our predicted B0 plus B1 x1, etc. is, there's a unique probability corresponding to that. So basically, to fit a logistic regression model, in a regular regression model, we tried to choose a set of B's to minimize the sum of squared errors between the predictor and the response. Logistic regression, you do something similar. You try to find regression coefficients such that your estimated probabilities are as close as possible to your observed probabilities. The details are way too hairy for an introductory class and don't really matter for us. We can just punch the numbers into R, and R will automatically calculate this. And so this raised the question, why are we bothering with this? Given that we have t-tests that say you want to predict the probability of having a heart attack given a person's cholesterol level, for instance. Well, we already have t-tests that we could take the cholesterol levels of people without heart attacks, cholesterol levels of people who had heart attacks, do t-tests to compare the two, and calculate a p-value to test the null hypothesis of no difference. Why don't we just do that rather than messing with logistic regression? And it turns out, if you just have a single binary variable and one quantitative response variable, usually logistic regression t-tests will give virtually the same results. There'll be some minor differences, but it's very rare to see noticeable difference between the two. But the main advantage of logistic regression, well, there's two of main advantages. Number one is if you have more than one quantitative response, then if you have more than one quantitative response, more than one quantitative predictor variable, there's no obvious way to do a t-test if you have more than one variable, but logistic regression is perfectly happy to take more than one predictor variable. You can test the null hypothesis that neither variable is associated with the response, or say that one variable not the other is, or whatever the case may be. And logistic regression also allows us to estimate the probability of the response for any given set of x's. recall this example I've used a couple times in the class. We're trying to identify risk factors for having a low birth weight baby. That this data was collected from a real observational study to see what things are associated with having a low birth weight baby, and they looked at 189 risk factors and considered or 189 babies, and looked at the following potential risk factors, namely age, weight prior to pregnancy, race, smoking, whether they've had any premature labors in the past, hypertension, or urinary irritability, and the number of physician visits in the first trimester. And the objective was to try to predict the probability of having a low birth weight baby based on these various variables. And there may also be secondary questions of interest here, that is smoking associated with lower birth weight once you take all these other variables into account. So to fit this model in R, this data set's called B-weight. I put a copy of it on Sakai. The R command to fit a logistic regression model is very similar to the command for ordinary linear regression. Recall, for ordinary linear regression, the command was called LM. To fit a logistic regression model, instead of LM, it's GLM. Then you give it a formula object, just like we did in the case of regular regression. We say low twiddle dot. Recall that a formula object with a dot in it says predict low. In this case, the variable low is a 0, 1 variable that's equal to 1 if it was a low birth weight baby and 0 if it wasn't. Given this data set, and then the last command is family equals binomial. Family equals binomial tells R that you want to do logistic regression. There's various other family commands to do various other types of regression, but we won't be covering those in this class. And the output is the output you can interpret just basically the same way that you would interpret an ordinary least squares model. In particular, these p-values over here is the p-values for testing the null hypothesis that a given regression coefficient is equal to 0. So for example, age, the coefficient is about minus 0.0723. Associated p-value is 0.336. So after adjusting for all the other variables in the model, we fail to reject the null hypothesis that there's an association between age and low birth weight babies. Now, maybe I should have set a slide up differently so this doesn't confuse anybody when the final comes around, but this does not imply that there is no association between age and having a low birth weight. It just says that once you take all these other variables into account, the effect of age is no longer significant. If you just want to know, is there any association at all between age and having a low birth weight, you should look at age by itself. Probably just do a t-test to compare the ages of the mothers of low birth weight babies to those without low birth weight babies. If that t-test is significant but this logistic regression model is not significant, then what that tells you is that maybe women, younger mothers tend to have lower birth weight babies, but that's explained by the fact that younger mothers are more likely to smoke, less likely to go to the doctor, or whatever the case may be. At any rate, you can see it puts stars on the things that are significant, that I forget what these various variables means. It looks like if the mother's white, then the probability of having a lower birth weight baby is lower than if for other races. Looks like if they have a history of preterm births And, gosh, I do not remember LWT and HT stand for. They're on the previous slide. See, hypertension and weight prior to pregnancy. There we go. So, looks like if the mother was underweight before she got pregnant, I guess that association is negative, so I guess I have to look at how this is coded, actually. There's an association between weight prior to pregnancy and having a low birth weight baby. It looks like what that's saying is that, yeah, if the mother's underweight before she gets pregnant, the risk of having a lower birth weight baby is higher. Likewise, if she's had previous low birth weight babies, the risk is higher, and so on and so forth. And in general, in R, if you say GLM, Y, twiddle X, that'll fit a logistic regression model to predict Y based on X. And Y either has to be a vector of zeros and ones, or it has to be a factor with exactly 2 levels. Or there's one other way that you can code this that can save you some time sometimes, that I'll show you here in a minute. And should also, if you look at the output, you'll notice that with ordinary least squares, it would give us an F statistic down at the bottom, testing the null hypothesis that every single one of the coefficients is equal to 0. The summary GLM command in R does not give us that, which honestly I don't entirely understand, because there's a simple analog of the F test, but for some reason R doesn't calculate it. The way that but if you want to calculate the p-value for the null hypothesis that all the coefficients are equal to 0, what you can do, as I'll illustrate in a couple slides, is you look at these numbers down here, the null deviance and the residual deviance. If you subtract the residual deviance from the null deviance, that should have a chi-square distribution with degrees of freedom equal to the difference between the numbers of degrees of freedom here. So in this case, it would have 10 degrees of freedom. If you take the difference between those two, you can use the chi-square command in R to test the null hypothesis. They're all equal to 0 simultaneously. So, I'll show you how to do that here in the next slide. Once again, we see null deviance 234.67 on 188 degrees of freedom, residual deviance 195.8 on 178 degrees of freedom. These deviances, they're sort of like the idea of residuals generalized to logistic regression. I won't bore you and confuse you with all the details on what those deviances actually mean, but the null hypothesis of interest here is that, well, under the null hypothesis that all the coefficients are equal to 0, the difference between the null deviance and the residual deviance should have a chi-square distribution with degrees of freedom equal to the difference between those 2 degrees of freedom. So, in this case, then, if the null hypothesis is true, 234.67 minus 195.48 is 39.19. That should have a chi-square distribution with 10 degrees of freedom. We can calculate the p-value for that test statistic using R. This p-value, it can sometimes be a little bit off. I think that's the reason that R doesn't calculate it automatically, but if you need to report your logistic regression model in a paper and they want a p-value, this should be adequate for that. So, the R command would be 1 minus p chi-squared, so we want the upper tail of the distribution, 234.67 minus 195.48 with 10 degrees of freedom. We get a p-value on the order of 2 times 10 to the minus 5. Fairly compelling evidence against the null hypothesis that all the coefficients are equal to 0. And also some comments on how to interpret the regression coefficients. This is another reason that people like logistic regression actually, is because of the interpretation of the coefficients. That, remember, in an ordinary least squares model, the interpretation of the coefficients are fairly straightforward. That if a variable x in your regression model has a coefficient of b, then you can, each time x increases by 1, y should increase by about b, assuming that all the other variables are held constant. And it's a little trickier to interpret logistic regression coefficients since we're calculating them on the log odd scale. But it turns out there is still a reasonably nice interpretation of the logistic regression coefficients, that in the when we fit a logistic regression model, if you want to do the math, you can show that if b is a logistic regression coefficient, then e to the b is equal to this quantity up here, which, if you can remember an obscure detail from a slide from a month or two ago, that's just the odds ratio for y between x equals 0 and x equals 1. So that means that when x increases by 1, the odds ratio for the outcome increases by a factor of e to the b. And odds ratios are nice because if you have a rare disease, it turns out the odds ratio is a very good approximation of the relative risk. Like smoking and lung cancer is a good example of this. Lung cancer is relatively rare, so the odds ratio and the relative risk are going to be almost exactly the same. So if you fit a logistic regression model to predict the probability of developing lung cancer given a dummy variable that's equal to 1 if the person smokes and 0 if it doesn't, then we get a logistic regression coefficient, and e to the b, e to that coefficient would be the relative, wouldn't exactly be the relative risk, it would be a very good approximation of the relative risk of smoking, which would be, if it were on the order of like 12, that would tell you that you're 12 times more likely to develop lung cancer if you smoke than if you don't smoke. And this only works if the disease is rare. People sometimes use it for other diseases, although they really shouldn't. If it's something extremely common, like, even heart disease isn't super common, but it's common enough that it would be a little bit dangerous to assume that the odds ratio of a family history of heart disease is equal to the relative risk. But as long as the disease is fairly rare, then this approximation will be fairly decent. So if we go back to the birth weight babies, the low birth weight babies example, we'll assume that the probability of having a low birth weight baby is fairly rare. In practice, I honestly don't know how common low birth weight births are, but if we assume that it's rare, that the odds ratio is a good approximation for the relative risk, you can take the coefficients of this model and then use the exp command as e to each coefficient, and then interpret the coefficients accordingly. What this says is that for every year older the mother is, the relative risk of having a low birth weight baby is about 0.96, or technically it's the odds ratio, indicating that the odds of having a low birth weight baby decrease ever so slightly as the mother gets older. Now, 10 years older, the difference would be 0.96 to the 10, 10th power no longer quite so negligible. These categorical variables are a little bit easier to interpret. Smoking is a binary variable that's either 0 or 1. If the woman is a smoker, then the odds ratio for having a low birth weight baby is about 2.13. Again, if we assume having a low birth weight baby is relatively rare, then women who smoke are about 2.13 times more likely to have low birth weight babies than women who don't smoke. And that's true even after adjusting for all these other variables. And if they've had a previous preterm delivery, the odds ratio is about 3.8. So if they had had a preterm baby in the past, they're about 3.8 times as likely to have another one, is how you interpret these coefficients. And as an aside, that's another reason that people like logistic regression as opposed to some of these other models. Logistic regression gives these nice interpretations of the coefficients. They're just the logs of the odds ratios. So you can take e to each coefficient and get estimates of the odds ratios. And as we saw in the logistic regression case, you go coef glm.object. It will give you the coefficients of a regression object, including the logistic regression object. If you go exp of x, that will give e to the x, where e, as you probably know, is 2.71828818, etc., etc. How do you interpret these coefficients? That the odds ratio is, for smoking, is 2.13. So, as I said before, we assume that having low birth weight is rare among non-smokers, then smokers are 2.13 times more likely to have low birth weight babies than non-smokers. And likewise, every 1 pound increase in the mother's weight prior to pregnancy will decrease the odds of a low birth weight baby by about 0.963. And you could also make predictions if using logistic regression model. In this case, the predictions, you would be predicting the probability of a given baby has low birth weight in the sample. If you just use the predict command in R, here I predict the log odds of the probabilities for the first 10 observations in this data set. It's a little bit tricky to interpret because they're on the log odds scale. So most of the time when you do this in R, rather than calculate the log odds of the response, you'll want to add this second parameter that says type equals response, which means that rather than predicting the log odds of having a low birth weight baby, it just gives you the raw probabilities. This tells you the first sample in the data set you predict to have about a probability of 0.297 of having a low birth weight. The second birth in the data set has a probability of 0.129 of having a low birth weight, and so on down the line. And if you say, in general, predict glm.object, that'll predict the log odds for each observation that was used to fit glm.object, and it can be tricky to interpret these log odds. Similarly, you can give it a new data command if you want to predict the log odds for an observation or observations in a new data set. And if you add the additional parameter type equals response, that will give you predicted probabilities rather than predicted log odds. Most of the time you're interested in the predicted probabilities rather than the predicted log odds. And one thing you have to keep in mind when you interpret these probabilities of having low birth weight or probabilities of anything using logistic regression is that if you have a case control study and you use type equals response to estimate the probabilities, they're only valid for the data set that you use to fit the model. The reason is that basically, this gets a little bit technical here. In a case control study, you can show that your estimated odds ratios are still valid. There is a famous paper on that, that the odds ratio for developing, if you calculate the odds ratio of having a low birth weight baby for smoking based on a case control study where you select a certain number of low birth weight babies and a certain number of babies without low birth weight, that odds ratio is still valid even though you didn't randomly sample from the population. But the intercept in that model will be way too high. If it's a case control study with an equal number of cases and controls and you just reach into your sample and pull a baby out, there'll be a 50% probability that that baby has low birth weight. Well, in the overall population, the probability is going to be much less than 50%. So if you just mindlessly apply the predict function in R to predict the probability of having a low birth weight baby on a case-controlled data set, it's going to wildly overestimate the probabilities because the data set used to fit the model has a lot more cases than in the general population, so it assumes the probabilities are much higher than they actually are. So if you do predict with type equals response on a logistic regression model that was fit to a case control study, you can only use those probabilities for the data set you use to fit the model. They won't generalize to other data sets that don't have as many cases in them. And just to show you one other way that you can fit logistic regression models, this is less common, but it can save you a bunch of typing in some situations. This is a data set built into R where they were trying to determine if smoking or drinking increased one's risk of developing esophageal cancer. And basically each patient in the study, they recorded their age and also whether they drank and whether they smoked. And so the data looks something like this, that they basically partition both age, drinking, and smoking into a series of bins. The age was 25 to 34. I don't know what the other categories were, but tobacco either has 0 to 9 grams per day, 10 to 19, 20 to 29, or 30 plus grams. Likewise, alcohol, they either had 0 to 39, 40 to 79, 80 to 119, or 120 plus. And for each of these bins, they counted the number who had esophageal cancer and the number that didn't. And if we tried to use the form of logistic regression model, or the form of logistic regression that we discussed previously here, that would have been a major headache. We would have to create a data set where these three observations are these three categories are repeated 40 times, these are repeated 10 times, these are repeated 6 times, etc., etc. Luckily, there's a way to do this in R that doesn't require us to simply create a bazillion repeats of each of these observations. Turns out that R is smart enough that for the response for a logistic regression model, it can also take a 2-column matrix where the first column is the number of cases and the second column is the number of controls. And in this case, we just say predict number of cases, number of controls. In other words, predict the probability of developing esophageal cancer based on age, alcohol, and tobacco. And in R, this output is a little bit weird. Basically, these ordered factors, L is the highest category for each one. What this seems to tell us is that if you're in the oldest age group and you drink a lot or you smoke a lot, your risk of esophageal cancer is increased. It doesn't seem to increase that much for any of the other categories. I mean, I find that it isn't common to use logistic regression in quite this form, but if you ever need to use it, those are the commands. In general, if you go GLM and a two-column matrix where one column is the number of cases and one is the number of controls, and that will be fit a logistic regression model with the specified number of cases and controls for each possible value of x. And one other thing to keep in mind when fitting logistic regression models, every so often you'll fit a logistic regression model and you'll get output that looks something like this. You'll see this warning message down at the bottom. It says algorithm did not converge, fitted probabilities 0 or 1. And if you look at the output, our p-value looks like it's catastrophic, but the reason why, you look at the standard error, and I mean it's ridiculously huge. It's on the order of 40,000. What on earth's going on here? Well, here's a graph of the data that I used to fit the model on the previous slide. And what's going on here is the x and y are completely separable, as we say. That if x is greater than 1, then y is pretty much always a 1. If x is less than 1, then y is always 0. So that implies that you can predict your outcome variable y with perfect accuracy on this model. So in this case, the odds ratio is infinite, which is why the model fails to converge, and why you get such a ridiculously huge standard error here. It's because every single time when R tries to approximate the odds ratio, just every single time it gets a bigger and bigger number, it finally says, okay, something's wrong here. So when this happens, I mean, this can be both good news and bad news. That implies that you're predicting your outcome with perfect accuracy, which tells you, despite the fact that your p-value is equal to 1, there's a ridiculously strong association between your predictor and your response. Like I said, the odds ratio is infinite in this case, but your coefficient estimates and p-values will be wrong. So if you get that message when you fit a logistic regression model in R, that tells you that for at least some of the observations in your data set, you're making predictions with perfect accuracy, but you need to go through it carefully and figure out why you're getting those infinite odds ratios and what variables associated with what. And most of the caveats that apply to ordinary linear regression apply to logistic regression as well. That, for example, if you try to extrapolate outside the range of your x's, you can get yourself into trouble. If your x's are correlated with one another, you get multicollinearity, which increases your variance. The one difference between logistic regression and ordinary linear regression is that your error variance is never constant in a logistic regression model. It always varies according to the predicted value of y, so you wouldn't need to worry about heteroskedasticity in the same sense that you would in linear regression if you plot the variance of your errors versus the predicted y's. Now, you still can get an issue called over-dispersion, which means that your error variance is greater than it should be under your theoretical model, but I sure as heck won't confuse you with that. I mean, I confuse myself with that. And if there's multicollinearity in your logistic regression models, you can use the same tricks that we did for ordinary least squares. In particular, the GLMNet package in R will allow you to use lasso or ridge regression in the context of logistic regression as well. So basic thing to remember today is that if you have a binary response and a set of predictor variables, you can try to predict the response based on the predictors using logistic regression. And here's the new R commands to do that. Any questions about anything today, homework, or anything else? Okay.